If humanity ever leaves the solar system, there are only a few realistic destinations. Most stars visible in the night sky are hundreds of light years away, far beyond the reach of any human exploration. But within the Sun's interstellar neighborhood, two systems stand out: Alpha Centauri and Barnard star. If we ever attempt to visit another star, these two are the most likely targets. So let's take a closer look at them, starting with Alpha Centauri, our closest stellar neighbor. The Alpha Centauri system is located 4.3 light-years away. Its name comes from the fact that it's the brightest star of the constellation Centaurus, a constellation in the southern celestial hemisphere. This system is not a single star. Rather, it's a system of 3 stars. The first component consists of a binary star system, whose members are called Rigel Taurus, not to be confused with Rigel, a bright star in Orion, and Ptolemy, collectively called Alpha Centauri AB, and their distance varies between 11 AU and 36 AU. The second component is Proxima Centauri, also called Alpha Centauri C, which orbits the binary star. Let's begin with the first component. Rigel Taurus and Ptolemy form the bulk of the mass of Alpha Centauri, consisting of about 95% of it. And they're both sun-like stars. Rigel Taurus has a mass 10% higher than that of the Sun, and is 1.5 times as luminous, and a spectral class of G2V. This is the exact same spectral class as our Sun, meaning that Rigel Taurus is essentially a slightly oversized copy of the Sun. With a magnitude of 0.01, it's the 4th brightest individual star in the entire night sky, after Arcturus, Canopus, and Sirius. Rigel Taurus is also believed to have a planet orbiting in its habitable zone, named Rigel Taurus B. This belief comes from a series of direct images from different telescopes showing the presence of some object, likely a Saturn-mass gas giant if it's a planet. However, astronomers have yet to confirm that this is a planet at all. Ptolemy is the smaller, fainter companion of Rigel Taurus. Its mass is around 90% that of the Sun, and is around half as luminous. As implied earlier, Ptolemy is also a sun-like star, albeit a bit cooler, with a spectral class of K1V. This places it in the category of orange dwarf, which is something of a middle way between yellow dwarfs and red dwarfs, as the name implies. Despite its smaller luminosity, Ptolemy is known to be more magnetically active than its companion. This means its surface emits a high amount of flares, similar to the activity that we see from the Sun. Unlike Rigel Taurus, Ptolemy does not have any suspected planets. With a visual magnitude of 1.33, and together with its companion, Rigel Taurus and Ptolemy appear as a single star with a magnitude of -0.27. It's a prominent site in the southern hemisphere and northern tropical latitudes. Let's now take a look at the third component of Alpha Centauri, Proxima Centauri. It's appropriately named because right now it's the closest star to the Sun. However, as mentioned in the beginning, Proxima Centauri orbits Alpha Centauri AB. It does so with a period of around 550,000 years. This means that a couple 100,000 years from now, Proxima will no longer be the closest star to the Sun. Rather, this title will alternate between Rigel Taurus and Ptolemy. Now, unlike the first two components, Proxima is not visible to the naked eye, but it is visible through a telescope. This faintness is due to its physical characteristics. It is not a sun-like star. Rather, it is a red dwarf with a spectral class of M5.5. This corresponds with a temperature of around 3000 Kelvin. It's quite a bit smaller and less luminous than our Sun. Proxima's mass is only around 12% that of the Sun's, and its luminosity is only 0.16% of the Sun's. But this is measured over all wavelengths, and because Proxima emits most of its light in the infrared, its true visual luminosity is only 0.006% that of the Sun's. Despite all of this, Proxima is significantly more active than the Sun and produces large, frequent stellar flares, and this doesn't bode well for its planetary system. There are 2 confirmed exoplanets orbiting Proxima Centauri, named Proxima b and Proxima d, and these were discovered by astronomers observing a wobble in Proxima's motion. Proxima b was discovered in 2016 and is of particular interest to the public given it's a rocky, Earth-mass, Earth-sized planet orbiting within Proxima's habitable zone. Whether or not this planet is actually habitable cannot be ascertained though, given that there is currently no way to determine if it has an atmosphere. Proxima d was discovered in 2022 and is a sub-Earth planet having a size and mass between that of Earth and Mars, and orbits very close to the star. This planet, for obvious reasons, is much less likely to be habitable on account of its high surface temperature. Our second target is Barnard star, located 5.96 light-years away. It was discovered in 1916 by American astronomer Edward Emerson Barnard, and this star is special for several reasons. The most immediate feature of Barnard's star is that it appears to move across our skies extremely quickly. In fact, in just a 180-year period, Barnard's star moves the apparent width of the Moon. With any telescope, this motion will be visible over a period of a year. What is the reason for this? As seen from Earth, every star in the sky undergoes something called proper motion. This refers to the apparent speed of the movement of the star through the sky over time. This movement is caused by a combination of 2 factors: the star's movement through space and the star's distance from Earth. For example, if a star is moving through space quickly but is extremely far away, its proper motion will be low. The same is true if the star is close to us, but moving through space slowly. The direction of the star's travel also matters. Is it moving directly away from Earth, or is it moving transverse to us? If it's moving transverse to us, it'll have a higher proper motion. Barnard's star happens to have 2 properties that lead to its high proper motion. It's very close to us, and it has very high transverse movement through space. Importantly, Barnard's star isn't moving through space faster than any other star, but rather, the direction of its movement and proximity to us makes it have a faster apparent movement than any other known star. Focusing more on Barnard's star itself, it's a small, cool red dwarf star, and physically similar to Proxima Centauri. Thus, it isn't visible to the naked eye, and requires a telescope to be seen. Its spectral type is M4V, corresponding to a surface temperature of around 3200 Kelvin. It has a mass 16% that of the Sun's, and luminosity of 0.04%. Like Proxima, Barnard's star is known to be very active, producing a high volume of stellar flares. In 2019, astronomers detected 2 individual far ultraviolet flares on Barnard's star with energies exceeding 10 to the 22 joules. If the sun were to produce those kinds of flares, it would strip away Earth's atmosphere within a few hundred million years. And again, this does not bode well for the star's planetary system. This star has been in the headlines several times over the last 10 years because it has gone from having planets in 2018 to having them disproven in 2021, and back to having planets again in 2024. Let's take a brief look at the history of Barnard B, for example, the first planet discovered to orbit it. In 2018, the discovery of Barnard B was announced and confirmed. At this time, it was thought to be a super-Earth mass planet orbiting at a distance of around 0.4 AU and an orbital period of 233 days. This is actually the same distance that Mercury orbits the Sun. However, because of Barnard's tiny size and luminosity, this distance also corresponds with Barnard's frost line, which is the distance where the temperature is cold enough for volatile compounds such as water, ammonia, and carbon dioxide to freeze solid. So at this distance, Barnard B would have been extremely cold with a temperature of around negative 170 degrees Celsius. All this being said, in 2021, this supposedly confirmed planet was actually disproven and shown to be a false positive. If you recall from earlier, we mentioned that Barnard is a very active and violent star, being a red dwarf. It would turn out that somehow, the measurements that were used to confirm the existence of Barnard B were actually detecting activity from the star itself, thus leading to a false positive result. But in 2024, a surprising study by Hernandez and collaborators proposed true, clean evidence that Barnard B really does exist, but that it looks very different from the original Barnard B. First of all, it's actually not a super-Earth. Rather, it's quite a bit less massive than Earth, having no smaller than around 30% of its mass. This puts it in between the mass of Mars and Earth. Secondly, Barnard B is not actually a cold planet, as was previously proposed. Instead, it orbits not at 0.4 AU, but over 10 times closer at 0.03 AU from the star, in just 3 days. This ultimately makes it a hot planet, with a surface temperature of around 125 degrees Celsius. And even better, the 2024 study also confirmed the existence of 3 additional planets orbiting Barnard. This system is extremely compact. The furthest planet, Barnard E, orbits only 0.04 AU away from the star, taking just under a week to do so. That's 10 times closer than Mercury orbits the Sun. Taking the star's small size and cooler temperature into account, this is still far too close to be in the habitable zone. So on the question of habitability, this system is hopeless. Additionally, all of these planets are sub-Earths with masses around 25% that of Earth, making them all slightly more massive than Mars. Thus, in the small chance that any of these planets had atmospheres at any point in their history, the star's high activity would have easily stripped all their atmospheres a long time ago, thanks to their relatively weak gravity. So the planets of Barnard's star are probably all similar to Mercury, barren, cratered, and hot worlds. We've seen these 2 neighbors, but as we go farther out, we see more and more systems. Some of these systems aren't even stars. For example, just after Barnard's star, at 6.5 light-years away, is Luhmann 16, a binary system of not stars, but brown dwarfs. These are essentially just failed stars. and going even further past 10 light years, we see Epsilon Eridani, a star with not only just a planet, but a fully developed debris disk and asteroid belt. As we go further from the Sun, the year we visit these systems gets exponentially pushed back. And while we will not live to see humanity visit Alpha Centauri and Barnard star, we lay the groundwork by learning as much as we can about these systems, as they will inevitably be our first destinations.